Hello! Welcome to this video from an undisclosed quarantine location in Oslo. Sorry about the poor quality of the video, if it is poor quality. I don't know how demanding you are. I want to talk about growth, because growth is an important topic these days, because we are very keen on trying to figure out how quickly the current global pandemic is spreading or growing. And when something grows incredibly fast, we usually say that it's growing exponentially. But I would argue that nothing really grows exponentially. Because when you're dealing with exponential growth, true exponential growth that follows an exponential function, the derivative or the rate of growth of that function is the function itself. So it's really infinitely increasing and never ending. And for any real world application that could never happen, I think. Not even if you had a laboratory with perfect conditions and you would grow bacterial samples or something in a petri dish, eventually the bacteria, they would run out of space, Another example is money in a bank account, which can be modeled with an exponential function, right? Ever accruing interest and compounding interest, growing and growing and growing, but eventually the bank would say that you have much money in this bank and we don't want you to be able to suddenly pull that out and remove half our capital or something, Speaking of economic growth, this is a very interesting topic because what has fueled economic growth throughout history really is that we have developed better and better technology to do things more efficiently. And it is an interesting question, I think, and I will not get into that in this video. Can we continue growing the economy in perpetuity, essentially? So what I think I'll talk about is the logistic function, which is a function that models growth, but after a while it will plateau and stop. Some people call it the S-curve. So in this model I talk about logistic functions and their properties and their parameters, and then in the video following this I will go more into trying to fit cases of the coronavirus that we're seeing these days to the logistic function. That I've done in a video prior to this as well, but now I will try to be a bit more thorough. Alright, so a logistic function can be written like this. You have an exponential function and you have 1 plus an exponential function. And the first thing we're interested in is what values this function can approach, either when x tends to a very large number or when x tends to a very small or a negative number. So when x becomes very large, then these exponential terms, they will dominate, and this number 1 will be negligible. And then you see that you have the same expression both as the numerator and the denominator, and you get the value 1. In the other case, when x becomes a very large negative number, then these guys go to 0, and this 1 becomes important. Then you simply get 0 divided by 1, which is 0. And as you may see, you are able to simplify this function a bit so that it becomes 1 over 1 plus e to the power of minus x. And the shape of this logistic function is the very well-known S shape, right? So it approaches asymptotically the value 1 in this case and goes from 0 and centered around 0 usually. We can add a bunch of parameters to this function. So let's rewrite this as f of x, and then we have parameters. I usually write a, b, c, d, but they can be called something else as well. A I usually put there, and you have a constant term, b, 1 plus e to the power of minus c times x minus d. And now we are going to be looking at how the function behaves when you change these parameters, and you'll see how one can fit the logistic function to some interesting cases. Alright? Okay, so here I have an empty file. First, what I want to do is I want to import NumPy, SMP, and I probably also want some plotting tools. So from matplotlib, import pyplot as plt. Alright, and then we'll define the logistic function, which will take parameters x, a, b, c, and d, and we'll simply return 1 divided by a divided by 1 plus np.exp minus c times x minus d, oh sorry about that, and then plus b, and that should be it really. Now let's find some values that we can input for values as these parameters. So the most common parameters to turn this function into the first one that I wrote, a would be 1, b would be 0, c would be 1, and d would also be 0. We are going to be changing up these values from, let's say, -2, -1, 0, -1, and 2. Yeah, that'll do. So let's start with a. For a in these values, what happens to logistic function? But we'll also need some x's. So I'm going to use a linspace from -6 to 6. So we are going to plot x of the logistic function, insert an x and the a, and we'll also add a label, which would be what the a value is, right? So we'll see what happens with that. A equals to a, and then we will going to have a legend, and then we'll show the entire thing. Alright, so there you go. So there you see what the a value does. Here is a equal to 2, so there we see that we approach the value 2, and here, down here, the blue one, a is equal to -2, and there we approach the value -2. So we could have predicted that really. Now let's look at the b's, the constant term. So the prediction now would be that the constant term just shifts the function up and down, right? Instead now we'll say that this is, let's be quick about it, we'll just do b equals a, and we'll put b there, fast. There you go. So we have 5 functions at different levels, and if we can get the y-axis there, we see that, yeah, they're equally spaced because the spacing between these are the same. What if we change the c value? So now we'll say that c should be this input. I hope you understand what I'm doing here, that I'm really just inputting these a's, which might be a bit confusing, for the c's, right? Well, voila! So now we have some fancy stuff going on. So what this does, it changes the slope of the function. Now if you remember, I actually have it up here so we can look at it for a while. So that's where the a was, which decided which value we approached. The b was the constant term, and the c is the one here. So c does something with the slope of the function. For a positive c, we get upward sloping curves, and for a negative c, we get downward sloping. And c equal to 0 doesn't have a slope at all. And if we increase the absolute value of the c, then we get a steeper slope, I think. Yeah, so this is a 2, it's steeper than the red one, which is a 1. And what happens if we change the d, which is our last term? Let's see if we can predict and see what happens. So this changes all the x values, so I would think that it shifts the curve horizontally. Indeed, it does. So here we have 5 very similar curves from -6 to 6. They're all similar, but this one is just more flat to the left, and this blue one is more flat to the right. And you see, for a negative d value, we get shifted to the left. For a positive one, we get shifted to the right. So that's what that does. So that was a quick intro to the logistic function and the different parameters involved with it. Next video, we are going to fit it to some number of registered coronavirus cases in different countries. Stay tuned.